One of the most common ways of storing energy is of course the use of batteries. Batteries exist in many forms and flavors and in fact represents just one type of electrical energy storage principle. As compared to the mechanical and heat storage principles discussed in the previous videos, electrical storage is more simple since it does not involve mechanical conversion steps to retrieve the electricity. Here we will discuss three forms of electricity storage. The normal batteries that you use in cell phones and laptops store energy in solid electrodes. In contrast, the redox flow battery is specifically designed for large-scale applications, and in this case the energy is stored in a liquid electrolyte. In both cases, the chemical nature of the constituents is changed. The third form of storage is the capacitor. It is based on a physical storage principle. The energy is stored in an electric field. In a capacitor there are two metal plates that are separated by a non-conducting substance. The non-conducting substance can be as simple as air. You store energy in the capacitor by applying a certain potential, for instance by attaching a battery. As a result, negative charge will collect on one plate and positive charge on the other plate of the capacitor. The amount of electrical charge that is built up determines the amount of energy you can store. A capacitor is characterized by the capacitance, the amount of charge stored on the plates divided by the potential difference between the plates. The amount of energy stored in a capacitor equals E 1/2 times the capacity times the potential squared. When you want to use the energy again, you connect the two metal plates and the electrical charge is released. The big advantage of a capacitor is that it can generate an enormous amount of power, albeit for only a short amount of time. The large power that is achieved is due to the fact that the energy is generated by redistributions of electrons only. This only takes a few seconds. A battery is a bit more complicated than a capacitor because it also involves electrochemical reactions. Electrical charge changes the chemical nature of the electrodes. Inside a battery there are two electrodes, a positive one called the cathode and a negative one called the anode. They are separated by a solid or liquid electrolyte. This is a substance that allows the diffusion of ions but is impermeable for electrons. On discharging the battery, at the anode a chemical reaction takes place that releases a positive ion to the electrolyte. This ion travels through the electrolyte while simultaneously an electron is released to the external circuit to provide power. The electron and the ion recombine again at the cathode surface. On charging the battery, the reverse occurs. This process is illustrated by this picture of the most simple version of the lithium-ion battery. On discharging, positive lithium ion from the lithium metal anode dissolve in the electrolyte, while electrons are released to the external circuit. Lithium ions move from the anode to the cathode through the electrolyte. At the cathode, the lithium ions react and are absorbed by the host material, while the electron is used for charge compensation. The output voltage of the battery depends on the difference in energy of the lithium being in the metal or in the host compound. The capacity of the battery is determined by the number of lithium ions that can be shuttled between the two electrodes. The stored energy equals the potential difference V times the number of shuttled ions times the charge of a single ion. The power of a battery depends on the current density that can be maintained at the electrode surfaces. Note that on repeated cycling, the metal electrode surface may form dendritic structures. This may create a short circuit within the battery, thus limiting the battery lifetime. Comparing the energy density of batteries in terms of volume or weight, we observe the improvement brought about by lithium-ion technology as compared to the other technologies, such as the familiar lead-acid battery that is used in most cars. However, this improvement has taken around 100 years. So it's not that simple to improve the energy density of batteries any further. Note, however, that a large proportion of the so-called dead volume and weight is due to things like the encasing of the battery. A redox flow battery is different from a normal battery. In this case, the storage functionality is decoupled from the electrode at which the reaction takes place. How does it work? Well, we have two compartments separated by an ion selective membrane, each containing an electrolyte and an electrode. The electrolyte contains vanadium ions in different charge states. At the right we have mainly 2+ ions, and at the left we have mainly 5+ ions. This is an out of equilibrium situation. Hence, at the right electrode, vanadium 2+ reacts to form vanadium 3+, donating an electrode to the electrode. At the left electrode, vanadium 5+ ions form vanadium 4+ by accepting an electron from the electrode. To prevent the electrolyte from becoming charged, protons, in this case hydrogen ions, move through the membrane from the right to the left compartment. The liquid electrolyte is now the storage medium. As a result, it can be separated from the electrodes and stored in separate vessels. Thus, the energy storage is decoupled from the power. The electrode reactions determine the power of the battery, but the amount of liquid determines how much energy the battery can store. In general, this makes it easier to store large amounts of energy. However, the energy density of the liquid is very poor, resulting in a large storage footprint. Nevertheless, several plants are running demonstrating over 14,000 charging cycles. Now we compare the electric storage systems that we discussed in terms of power and energy per kilogram. We observed that the low power and energy density of the redox flow systems, which is due to the low energy density of the electrolyte. The supercapacitor generates much more power due to the fact that the electrons may leave the capacitor plates at great speed. As compared to this, in batteries, more energy can be stored per kilogram material. As compared to the capacitors, much more ions can be stored in the battery electrolytes. This is due to the fact that the ions are charge compensated. Remember, however, that even in batteries, the storage capacity is limited to around 100 to 200 Wh per kilogram.